Welcome to a new lesson of heat transfer. Today we talk about the entrance region. So we consider a circular pipe and we ask ourselves what happens to the velocity field and the temperature field as the fluid enters the pipe. Of course, this is important because we want to compute the friction and the heat transfer when the flow is still not fully developed. So let's start with the velocity field near the entrance of the pipe. So as the flow enters the pipe, here we are zooming in near the pipe wall, the velocity is uniform. As the flow develops over the surface, we have a no-slip condition. So the fluid particles stick to the surface of the pipe and we have a boundary layer that develops on the surface of the pipe. So in the entrance, the situation is quite similar to an external flow, and we studied how the flow develops, how the viscosity affects the momentum transfer near the wall. So as the fluid particle stick to the surface of the pipe, then of course near the wall in the boundary layer the flow is slowed down, and because of conservation of mass then the flow must accelerate in the core, so far away from the pipe, near the pipe axis. So in general, we have a situation where the velocity profile that develops downstreams depend on x, the coordinate along the streamwise direction, x, and also along the wall normal direction, r, the radius. So this is a typical sketch of the velocity field near the entrance. So these two lines define the growth of the boundary layer from the entrance of the pipe. So in this region here, and here, we have the boundary layer, so the flow is affected by viscosity. Whereas in the core, the flow can largely be assumed to be inviscid, so viscosity plays no role. Then the viscous region thickens and the flow develops downstream because momentum diffuses due to viscosity. And then eventually the boundary layer merge, and we have far downstream a region where viscosity plays a role everywhere at any location r and x. So we can define a hydrodynamic entrance region. So that's the region where the flow is not fully viscous, so there is an inviscid core. And then we have a region that's hydrodynamically fully developed, where the flow is affected by viscosity everywhere. The velocity profile does not depend on x, where here the velocity profile depends on r and x as well. Keep in mind that in the viscous core, there is, of course, the pressure gradient that makes the flow accelerate. The pressure gradient in the hydrodynamically fully developed region is a constant, but the PdX in general instead depends on x in the hydrodynamic entrance region. So in the same way we study the velocity in the entrance region, we can study the temperature field near the entrance. So it's similar way we can define a thermal entrance region and a region downstream that we can define thermally fully developed. So we can define a thermal boundary layer develops downstream. That's a region where the temperature gradients are important, where the heat transfer will occur, whereas in the central region, the gradients of the temperature are very small. So eventually in the thermally fully developed region, the heat transfer effects occur everywhere because we have temperature gradients any location x and r. But there is a key difference between the velocity field and the temperature field in the entrance regions. So the velocity Vr does not depend on x when fully developed conditions are achieved, whereas the temperature field in general depends on x, but we define the fully developed thermal region when this non-dimensional ratio does not depend on x. So this means that in fully developed conditions, the shape of the temperature profile remains the same, but the temperature may increase or decrease depending on whether we heat the flow or we cool the flow. So mathematically, we can define an hydrodynamically fully developed region when the partial of the velocity profile with respect of x, partial derivative, is 0. So the velocity profile only depends on r. So we're always talking about the laminar flow. In the thermally fully developed region, then instead the partial derivative with respect to x must be with respect this non-dimensional profile. It's important, of course, to define a friction factor. So again, the friction factor is skin friction factor is the wall shear stress in any location x over the pipe non-dimensionalized by 1/2 rho ub, or VB actually. So VB is the mean velocity, also called bulk velocity. So defining in this way, since VR, the velocity profile, only depends on R in a fully developed region, then CF, the skin friction coefficient, is constant. We must also define a heat transfer coefficient H. So we recall that QS, the heat flux at the wall, is equal to HX times a difference in temperature, so the temperature at the surface minus a mean temperature, and we define it with the Fourier's law of conduction. So, but this ratio we see in the fully developed conditions that does not depend on x. Then also the partial of this quantity with respect of r will not depend on x. So we find this quantity, but this quantity multiplied by k is nothing but the heat transfer convection coefficient. Therefore, this quantity, so Hx, is constant in thermally fully developed region. In laminar flows, it's very interesting to compare the entrance length. And for this, we use the Prandtl number. Prandtl number, we recall, is the ratio between the kinematic viscosity and thermal diffusivity. It's a non-dimensional numbers because these quantities represent different physical phenomena but have the same units. It's interesting because Prandtl number is, of course, a number that depends on the property of the fluids, but reveals very important information about convection. So when the Prandtl number is about 1, these two quantities, the kinematic viscosity and thermal diffusivity, are comparable. This means that the two boundary layers that develop over this surface of the pipe in the entrance region, so the kinematic or velocity boundary layer and the thermal boundary layer, grow at the same rate. And the growth and the thickness of these two quantities is regulated by the kinematic viscosity in the velocity case and by the thermal diffusivity in the thermal boundary layer. So this means that the entrance region are comparable. But now let's think about the two extreme cases when the Prandtl number is very large and the Prandtl number is very small. So we're always talking about laminar flows. So when the Prandtl number is very large, in case of oils, for example, very viscous fluids, of course, then the velocity boundary layer grows much more than the thermal boundary layer. This means the hydrodynamic length is much smaller than the thermal length because viscous effects, so the momentum transfer, occurs much more quickly at a shorter distance than the transfer of heat. In the case, instead of Prandtl number very small, much smaller than 1, liquid metals, they are great conductors, but they're not viscous, very much viscous. So we have the thermal boundary layers that grows much faster than the velocity boundary layer. This means the thermal length for liquid metals is much shorter than the hydrodynamic length. So what happens to the skin friction coefficient, the heat transfer convection coefficient at the entrance of a pipe? Well, they have a very similar behavior in the fully developed regions. So after we have passed the hydrodynamic entrance length for the friction coefficient or the thermal entrance length for the convection coefficient, these two quantities are constant, but in the entrance region, both the skin friction coefficient and the heat transfer coefficient are larger than the fully developed values. So we talked about the laminar flow, and so we can actually quantify this. So the entry length, so the length of the entrance region, the hydrodynamic case or velocity case, is equal to 0.05 times the Reynolds number based on the bulk velocity and the diameter times the diameter itself, and the length of the thermal entrance region is the same formula, but now we have to multiply by the Prandtl number. And if you note here, the ratio of these two quantities is precisely the Reynolds number as we discussed before. We're not studying the turbulent case in detail, but we can just remember that the two entrance lengths in this case are comparable, is about equal to about 10 diameters. So thanks a lot, and I'll see you in the next lesson.